part 2 of the lecture. So here we're going to look at the dose-response relationships. And that's just to tie this up. So the dose-response relationship for stochastic effects isn't as clear as it is for deterministic effects. Epidemiological studies can only provide statistical associations between dose and effect. So the problem here is that because it's statistical, it varies, there's large uncertainties, and we simply don't have statistics or reliable statistics for very low doses. So this will become evident as we go through the slides. So, radiation-induced cancer at low doses. At very low doses, the risks are not very clear. But they are important because low doses include cancer screening and just general X-rays, occupational exposures, they're low exposures, and industrial situations like nuclear power plants. So how do we estimate the risk of radiation-induced cancer? So we use the dose-response curve from the survivors of atomic bombs, so that is some data that we use, but we also use other data as well, and we'll go through that in a few moments. The main source is the atomic bomb survivors, and so this is taken from what's called the lifespan study. And it's the survivors of the Japanese Hiroshima and Nagasaki bombs in 1945, and they provide the best statistical data. It's because it's the largest group of people available, and the dosimetry is reasonably reliable because the participants in the study sort of remember where they were standing when the bomb went off. And from that they can calculate distances and doses and whatnot. So the mean dose in the exposed group was about 200 millisieverts, with more than 50% of the cohort receiving less than 50 millisieverts. And this is compared with individuals who receive less than 5 millisieverts, so people who were further away. So risk estimates in stochastic effects are given normally as if 1 million people were given 10 millisievert dose per year. So it's normally a percentage per 10 millisieverts per year. And you'll see when we come to it. Alright, so the models for dose response relationships, and we'll come to some of the statistics to make up these models a little bit later on. So there's different sorts of models. So here are the different types of possibilities. So we could look at what we have on the x-axis here is the dose, and then on the y-axis is the cancer risk, or the probability that cancer will occur. So the first model that we look at is what's called the linear no threshold model. So that's this line A here, and it's linear because it's a linear line, no threshold, so it starts at 0, and that's basically it. So it's just a linear extrapolation and based on the large amount of statistical data. Another possibility might be this curve B, this dotted curve here, what's called the downwardly curving model. And there's some possibility of this being correct as well, and it could be associated with a small number of hypersensitive individuals at low doses, so they have a greater probability of having cancer at low doses, or it could be associated with a priming radiation dose, so an unknown radiation dose, or possibly bystander effects. Curve C is pretty much the opposite of the previous one. So this is gives a good description for induction of leukemia and chromosome aberrations. Curve D is threshold, so curve D here is linear but has a threshold. So this assumes that there's you can take a certain amount of dose before your risk starts to increase, and so that matches some induction of sarcomas. So that's cancers in connective tissue. Or curve E, like a hormetic relationship, which actually goes negative at low doses, which means that the model suggests that at low doses of radiation might actually be good for you. So those are the different possible models that can be considered at the moment. The one that the ICRP uses, and so all legislation and science is based on this at the moment, is the linear no threshold model, so this curve A here. So that's a standard model, and based on this model we say that at 0 doses, 0 chance that a person will get a radiation-induced cancer, which is pretty obvious, because if they have 0 dose they haven't had any radiation. But as you increase the dose, the chance of getting a cancer increases linearly with dose. There's some assumptions here. The assumption is that there's a constant probability of mutation of a cell per unit dose, and so any radiation dose is potentially harmful. It assumes that the radiation dose is not repairable, so any DNA breakage has the same probability of causing cancer, independent of the number of other lesions. So that assumes that there's no repair. The probability of biological damage has a linear relationship with the absorbed dose. The LNT model describes the relationship between of doses from about 0.2 to 5 sieverts fairly well, but extrapolation is needed to go outside of that range, and there's a lot of errors basically, and you'll see this when we get to the data. But for now, the LNT is remaining as the standard model. But there are doubts about the validity of the LNT model, and you can find this on the internet. You can find discussions about this. So there's recent advances put down on this. For example, cells aren't passively affected by the accumulation of radiation or lesions. They react against oxygen species. They can eliminate injured cells, and they can do DNA repair. But there are doubts. At doses less than 10 millisieverts, lesions are eliminated by cell death. Higher doses, there's a significant number of cells can be damaged, but there's repair mechanisms. At low doses of less than 100 millisieverts, the amount of misrepair is small, but it's important. Importance per unit dose increases with total dose and dose rate. Low dose rates, the probability of misrepair is smaller. With the LNT model, is there actually a dose threshold for ionising radiation induced cancer? That's not. It's assumed at the moment, but it's and it's just assumed through prudence. Is radiation damage repairable? Well, details of the effect are unknown, but high dose rates are more effective in inducing cancer. And what's the relationship between the dose and the LET for low doses of ionising radiation? This is not quite fully understood yet. So there's scientific debate about the LNT model, and it's based it's based on epidemiological data and carcinogenic risks in about the 0.2 to 5 sieverts. But the doses received in medical imaging, which is most of the deliberate radiation dose given out throughout the world, it's actually much lower than the models or the doses available to the model. So at the moment, yeah, it's all still pretty up in the air, but it's assumed that the linear no threshold model is the correct model for the time being. So let's look at some studies at the low doses. So the largest group to study is the atomic bomb survivors from the lifespan study. Now, if you guys do a Google search for lifespan study, you will find the RERF site, Radiation Research Foundation site, a Radiation Effects Research Foundation site based in Japan, and they have lots and lots of documents and data. There are tens of thousands of survivors of the atomic bombs, and they can be traced, so they know the radiation dose. This is just a repeat of the previous, well, not previous slide, a few slides back, mean dose 200 millisieverts. Most of the people receive less than 50 millisieverts, and the data is compared to those who receive less than 5. So let's start looking at a bit of data here. So this is, the next slide is the risk of getting solid cancers from A-bomb survivors, atomic bomb survivors. So here are the doses here. So these this is on this axis. This is the excess relative risk. All right. So this is the fraction increase of, or the fractional increase of the probability of getting cancer compared to a person who wasn't exposed to this radiation. And we've got the dose range down here. So if you have a look at this, we've got some data points here, and you can see we've got like huge error bars, all right, and the linear no threshold model data fits right in that line there. So you can see that this data is not actually very well fitted to the model, but this is what feeds into the linear no threshold model. So this is for solid cancers among survivors in the LSS group.